When a singer steps up to a microphone and hits a note, they are creating physical energy. That energy ripples through the air as a perfectly smooth, continuous wave of pressure. This natural, flowing energy is called an analog signal. Because it moves without any breaks or interruptions, a single second of that sound wave holds an infinite amount of microscopic detail. But computers can't handle infinity. A computer brain is entirely mathematical. It doesn't understand smooth curves or flowing physical energy. It only understands rigid, exact numbers, specifically ones and zeros. Imagine trying to build a perfectly curved skateboard ramp using only rigid, rectangular building blocks. No matter how carefully you arrange them, you can't create a perfect curve. You can only build a staircase that mimics the shape of a curve. To store music, a computer has to do exactly that. It takes that perfectly smooth analog wave and rebuilds it from scratch as a rigid mathematical staircase. To start building this staircase, the computer has to freeze time. It does this by taking incredibly rapid, sequential measurements of the sound wave as it passes by, almost like a camera taking high-speed photos. The number of these snapshots the computer takes every single second is called the sampling rate. If you listen to a standard audio CD, the computer is playing back 44,100 individual snapshots for every single second of music. These rapid-fire snapshots track the forward timeline of the song, acting as the horizontal foundation for our digital staircase. Mapping out time gives our staircase its length, but it doesn't give it any shape. To actually see the wave, the computer also needs to know exactly how tall each of those 44,000 steps needs to be. At every single one of those snapshots, the computer measures the exact height of the sound wave at that moment. In audio, we call this height the amplitude. To get this measurement right, the computer uses a vertical digital ruler. The precision of this ruler is defined by its bit depth. The more bits we have to work with, the more markings we can fit onto the ruler. If the ruler has very few markings, the computer is forced to guess. When the actual sound wave hits between two lines, the computer rounds the measurement to the nearest one, creating a staircase with massive, chunky, jagged steps. Standard high-quality audio uses 16 bits. Because every extra bit doubles the number of available options, we end up with a ruler that has over 65,000 microscopic markings. With that many choices, the staircase steps shrink down so small they trace the original curve almost perfectly. This diagram shows that exact relationship. You can see the flowing blue curve of the original sound forced into the rigid orange blocks of the digital world. Each block is one specific, exact choice on that vertical ruler. Having those 65,000 choices is what prevents rounding errors. It's the reason high-quality digital audio sounds clear and natural, instead of sounding harsh, metallic, or broken. For you, the listener, this vertical precision creates what's called dynamic range. Dynamic range is simply the space between the absolute quietest sound and the loudest sound a file can hold. A large range allows a single song to preserve both a deafening drum crash and a whisper-quiet breath without losing any detail. On the left, physical sound hits a microphone, entering a box that turns smooth vibrations into rigid numbers. To hear the music, the computer reverses the trick on the right, translating those numbers back into electricity to push your speakers. The final magic trick of digital audio is actually performed by your own brain. Because the sampling rate is so fast and the bit depth is so precise, the digital steps are too small for your ears to notice. Your brain naturally smooths over the edges, leaving you with nothing but the illusion of a perfect, continuous song.